Here we are with nitrogen trifluoride, and you're supposed to figure out the shape of this molecule. It's different than boron trifluoride in that we've got nitrogen, which tends to end up having an octet. You should be able to do the Lewis dot diagram for this very, very quickly. We've got our nitrogen with its 5 valence electrons and our fluorine with 7. One of those being fluorine, here it is, with 7, one of those ready for bonding. And so a total of 5 plus 3 times 7, 26 electrons, 3, 4, 6 each bond, and then our surroundings 6 at a time, 18, leaving 2 for the central atom. And this is where things are different. We've got an extra cloud of electrons here, which are going to significantly change the shape of this molecule. Typically on an AP exam, they're going to ask you for shapes of molecules, 2-3 points sometimes on an exam. So this might be 2% of your AP exam. The shape that they show you will be the flat two-dimensional version, and it's going to be wrong. You almost never, ever get 90-degree angles in a molecule, with a few exceptions. But if they show you an angle on a two-dimensional drawing, you know that's going to be wrong. You're going to need to know how many bonds we have, how many pairs of electrons, and how many domains to figure out the shape of the molecule. So we have 1, 2, 3 sigma bonds, 3 shared pairs, 3 bonds, and 1 unshared pair, 4 domains. So remember that, and let's flip over right now to our molecular shape table, which is going to be used as our method of finding the shapes of molecules. Now on the left-hand column, we've got the steric number. Now here we've got a steric number for a hypervalent, where you've got lots of electrons, more than an octet, and they're the only ones that have 90-degree angles. None of the others do. Steric number of 6, steric number of 5, you've got some 90-degree angles, but also 120 along our axis here. And here's the more normal atoms that aren't hypervalent, that have our regular octets, where we've got 2, 4, 6, 8 pairs of electrons, some in bonds, some in not bonds. If you remember, our steric number was 4, so this is the row with the possible shapes. And we only had 3 bonds, so therefore it would be a trigonal. It's got sort of like a triangle, but it's a pyramid. So a trigonal pyramidal, nice logical name. 3 bonding pairs, 1 lone pair of electrons. Notice all the angles are 109. If you remember the balloon analogy, this is the best way for electrons to repel one another in 3-dimensional space, 109 degrees roughly. Also, when you end up having 4 domains, you end up having what's referred to as sp3 hybrid orbitals. And sometimes they'll ask about what type of hybridization we have. And the critical thing to know about hybridization is that it depends on the number of domains you have. 4 domains is called sp3 hybrid. 3 domains is sp2, and 2 domains is sp. Imagine superscripts here. We have a superscript 1 and a superscript 1 that adds up to 2. So that's a good way of remembering things. And we've got the associated shapes, linear, trigonoplanar, as we had for boron trifluoride. And in this case, the more common one, the sp3. In fact, we've got 3 clouds of electrons, and all at roughly 109 degrees. Each one of these orbitals is called an sp3 hybrid because it's a combination of s and p orbitals. So, okay, that takes care of a couple of really critical questions. Let's get back to the diagram that I have here and give that arrangement here. Here we've got 4 domains, an expected angle of 109 degrees. We'll work on that a little bit. But there's one other thing, and that is the symmetry. This is considered to be an unsymmetrical molecule because we have this cloud of electrons here. Now, fluorine, again, as I mentioned before, has a huge electronegativity. And in this bond, you'll remember, it's going to tug away at the shared, there's a shared pair of electrons here, and the fluorine is going to have an advantage over the nitrogen, which has a electronegativity of 3. Fluorine has the highest electronegativity. If you want to remember 3 of them, fluorine, the highest electronegativity, oxygen, the second highest, and nitrogen, the not quite as much, but still pretty high at 3.1. So again, we've got this fluorine pulling down and this fluorine pulling down. There's no counter fluorine pulling up. So the net result is that there's going to be a final electronegativity. I'll get rid of this one here. This is the resultant, if you're into vectors, of this tug of war, where the final result is that we'll have a slight negative charge at the bottom of this molecule. I'll put a minus here. And a slight positive charge up here. It's a polar molecule, and I probably should have put parentheses on here because it's not a full charge. It's a partial charge, a dipole. So this molecule has a positive and a negative side to it. That'll come in later when we do intermolecular attractions. So an unsymmetrical molecule almost always will have a deviation in its charge, or I should say a separation of its charge. That's natural for this molecule. Okay, next let's go to the one other little twist that's on here. The experimentally determined angle is really 102. Remember that the predicted is 109. This is a little bit smaller, and the rationale that they give is that this cloud of electrons up here is sort of fuzzy and large and is more repulsive than these three fluorines. So the angle is smaller. I have my doubts about that. I think the rationale is not really that accurate, but that's what is expected on the AP exam. So remember that as your rationale, but like I say, don't take it as being absolutely true, because there may be some evidence to indicate that it's an iffy explanation. Okay, there we go. There we've got our molecular shape of nitrogen trifluoride and its polarity, having a dipole and a slightly smaller angle that we would expect for the answer for this. Okay, there we go. Nitrogen trifluoride.